Hey everyone, and welcome. We're about to do a quick flyby of Chemistry Chapter 18, which is all about the representative elements. These are some of the most important and useful elements out there, so let's get right into it.
It's a great question, right? And the answer is they're both all about the representative elements. You've got silicon powering the chip in your phone, and you've got nitrogen and oxygen in the air you're breathing right now. These elements are quite literally the backbone of our world.
So here's what we've got on tap. We'll start with a quick overview, then we'll hit the essential vocabulary to make sure we're on the same page. After that, we'll take a tour through the metals, metalloids, nonmetals, and finish up with those interesting groups at the very edges of the periodic table.
All right, so first things first, what's the big idea behind this chapter? Well, it all boils down to the representative elements. These are the elements where the outermost electrons are filling up the s and p orbitals. You'll find these guys in groups 1, 2, and then all the way over from 12 to 18. And they cover the whole spectrum: metals, metalloids, and nonmetals. The most important thing to remember here is that their properties aren't random. They follow these beautiful, predictable patterns called periodic trends. And our ability to understand and tweak those properties, especially with an element like silicon, is exactly what makes all of our modern electronics possible.
Okay, before we get into the nitty-gritty, we've got to make sure we're all speaking the same language. Chemistry has a ton of specific terms, and knowing them is the key to really understanding the concepts. So, let's do a quick vocabulary refresh.
Now, I'm not going to read every single definition out loud. We'd be here all day. But what we'll do is display them over the next few slides. Think of this as your chance to pause the explainer, take a look, and refresh your memory on any terms that seem a little fuzzy.
So, here in our first batch, you'll see some fundamentals like acid anhydride and alkaline earth metal, and check out allotropes. That's a super cool concept. It's when you have different forms of the same element, like diamond and graphite for carbon. This next set is all about the processes. You've got things like chemical reduction, which is a key way we isolate metals. And then you see specific industrial methods like the chloralkali process and the downcell. These are huge deals in the chemical industry.
And here are some more heavy hitters. We've got the famous Haber process. We're definitely going to talk more about that one later. You'll also see definitions for common ions and compounds, like halides, which are super important when we get to group 17.
We're cruising right along. Now, this set is really important because it defines our main characters for the next section, the representative metals and the metalloids. Understanding these two categories is central to this whole chapter.
Almost there. This slide has a lot to do with oxygen, compounds like oxides and peroxides. It also brings in a really important biological process, photosynthesis, which, as you know, is all about chemistry.
And that's our last batch of terms. Awesome! Now that we've got the lingo down, let's see how all these pieces fit together. It's time to put this vocabulary into context by touring the different types of elements.
All right, first up on our tour, the representative metals and metalloids. These elements cover a huge range of properties, but what's really cool is that you can see these clear, predictable patterns as you move through the periodic table.
This slide really breaks it down nicely. You've got the superreactive alkali metals over in group 1, always wanting to form that 1+ ion. Right next door, the alkaline earth metals in group 2 have chilled out a little, forming 2+ ions. As we jump across the table, you see these patterns continue. A 2+ state for group 12, a 3+ state for group 13, and then things get a bit more flexible with elements like tin and lead.
Yeah, because these metals are so ready to party, chemically speaking, you're not just going to find a chunk of pure sodium sitting on the ground. They exist in compounds, so we have to isolate them. For some, like sodium and aluminum, we use electrolysis. For others, like magnesium and zinc, the go-to method is chemical reduction.
And now we get to the metalloids. Think boron, think silicon. These guys are so cool because they're the ultimate fence-sitters, bridging that gap between metals and nonmetals. And their most famous property, of course, is that they're electrical semiconductors. That little bit of magic is the reason we have computers, phones, and pretty much all modern tech.
Okay, so we've crossed that metalloid bridge. Now we're in the land of the nonmetals. And in a lot of ways, their properties are basically the mirror image of the metals we just talked about.
Just look at the differences here. Nonmetals have way higher electronegativity. They are real electron hogs. They're oxides. When they react with water, they form acids, which is why we call them acid anhydrides. And structurally, they're all about forming individual molecules, not those big shared metallic grids you see in metals.
All right, time for a lightning round. Let's hit some of the most important non-metal elements and their compounds. I'm talking about the real building blocks of life and industry.
First up, hydrogen, totally unique in a league of its own. Then you've got carbon, the basis for things like carbonates. Nitrogen, with that incredibly stable triple bond, is tough to crack, but vital for industry. Phosphorus gives us key acids like orthophosphoric acid. Oxygen, well, it's the life of the chemical party, super reactive and forming all kinds of oxides. And finally, sulfur, which loves to team up with metals to make sulfites. And speaking of that tough-to-crack nitrogen bond, that brings us to the Haber process. This isn't just an industrial reaction. It's one of the most important reactions on the planet. It's how we use massive heat, intense pressure, and an iron catalyst to finally force nitrogen to make ammonia, which is absolutely critical for making fertilizers and countless other products.
Okay, to wrap up our little tour of the elements, let's head to the far right edge of the periodic table. This is where you find the wild contrast between the super reactive halogens and the super chill noble gases.
And it really is a tale of two extremes. The halogens in group 17, they are desperate to react with pretty much anything. They'll form halides with metals or even react with each other to create interhalogens. But then you take one step to the right, to group 18, and you've got the noble gases. Their defining feature is that they don't react. And ironically, that very inactivity is what makes them so incredibly useful for things like inert atmospheres, those bright neon signs, and a specialized coolant.
So, that brings us to the end of our review. And I want to leave you with something to chew on. After running through all this, what's the one connection between an element's spot on the periodic table and its job in the real world that really just made you go, huh, that's cool? It's pretty amazing when you think about it.